So let us start where we left off the last time. We were looking at the conservation of angular momentum, and now I have in mind a system which consists of n bodies. So system of n, let us say, particles or masses, and this system moves under the effect of forces which each body causes on the others, or each mass causes on the others. So we have a system of Newton's equations, which is dp1 over dt is F12 plus dot 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 plus F1n, and so on all the way down to dpn over dt is Fn1 plus Fn2 and so on up to Fn minus 1. So here's the system of these n particles which are in interaction with each other due to some unspecified forces which are given by F12 right up to Fn comma n minus 1. Now we already saw that Fi j was equal to minus Fji. This was the third law. As a consequence, we saw that the sum of momenta of P1 to Pn, this is a constant of the motion. This implied that P equal to P1 up to Pn equal to a constant of the motion. In other words, this combination of momenta has exactly the same value at all instants of time as the particles move and change their individual positions as well as momenta, but this sum remains a constant of the motion. What else can we say? Well, we already saw last time that if I took r cross this quantity, then if I define the angular momentum L, the total angular momentum, to be equal to r1 cross p1 plus etc. plus rn cross p sub n. This is the total angular momentum about the origin. By definition, and I ask, how does that change as a function of time? Well, I would expect given no other information, that this too, if it's a closed system, not in interaction, no forces from anywhere else from outside acting on it, I would expect that this also will be a constant of the motion because there's no net torque on this system. But how do we prove this? Well, we need to compute its time derivative. So dl over dt equal to, and now dr1 over dt cross p1, which is 0 because dr1 by dt is the velocity of particle 1 and p1 is the mass times the velocity of particle 1. So that part is 0. The second part is r1 cross dp1 over dt. So this is equal to r1 cross dp1 over dt. Similarly, in the second term, the dr2 over dt cross p2 cancels and you are left with r2 cross dp2 over dt plus dot 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 plus rn cross dpn over dt. In other words, the net change of angular momentum is the vector sum of the torques on particle 1, particle 2, particle n up there. But dp1 over dt is given by this quantity here. So let us put that in, and we have this is equal to r1 cross f12 plus r1 cross f13 plus etc. plus r1 cross f1n. That takes care of just this first term, plus, and we have to write this for all the terms, plus r2 cross f21 plus r2 cross f23 plus etc. and so on. we can write down all these terms. We don't need to write all of them down because we can see the pattern immediately. Let me write just one more term, and that's the next line, which is plus R3 cross F31 plus R3 cross F32 plus etc. and so on. But we know from Newton's third law that F21 is minus F12. So if I put that in, this becomes R1 minus R2 cross F12. So I can recombine this and write this whole thing as dl over dt equal to R1 minus R2 cross F12. So that takes care of this term as well as this term, using Newton's third law, which says F21 is minus F12 vectorially. I put the minus sign on this R2 and take out an F12, and here it is. Similarly, this along with this term together with this term becomes plus R1 minus R3 cross F13. Again, using the fact that F31 is minus F13. Similarly, each time you have one term here, you have another term with the opposite sign, so you also have terms like plus etc., and then you have plus R2 minus R3 cross F23 and so on. But you see, Newton's third law is applicable. One of the conditions is that the force between the two particles acts along the line joining them. So if you have particle I here and particle j here, then this line joining the two of them, the force acts in one of the directions. Fij may act in this fashion, Fji may act in this fashion, for instance, or the other way about, it doesn't matter, but it's along this vector, along this line. On the other hand, if in some coordinate system this quantity is Ri and that vector is Rj, then you can see that this vector here is essentially Rj minus Ri, or written this way, it's equal to Ri minus Rj. So if you take this vector and add to it Rj plus Ri minus Rj, you get Ri by the triangular law of addition of vectors. So now we have a situation where in every one of these terms this force is precisely along the line of this vector, and therefore the cross product is identically 0. So again the input has been Newton's third law, and that's all that has happened. So each of these terms is 0, and therefore dl over dt is 0. So this says now that if the net torque on a system is 0, this implies that L is a constant of the motion. It does not say that individual L's R1 cross P1 or R2 cross P2 or the sum of R1 cross P1 and R2 cross P2. It doesn't say that these angular momenta are constants of the motion, just as in the case of the momenta. It says the total angular momentum is a constant of the motion as a consequence of the fact that Newton's third law cancels these terms out in pairs here. So as long as the force between two bodies is along the line joining them, you're guaranteed by Newton's third law that the total angular momentum of such a system of particles or bodies is going to be a constant of the motion. Again we ask, where does this come from? We already mentioned that the law of conservation of linear momentum arose because of the homogeneity in space. It doesn't matter, the actual location of the origin of coordinates doesn't matter. Where does angular momentum conservation come from? And I'll write this down. We won't prove it here, but I'll write this down. It says you have the potential for the conservation of angular momentum arises from from the fact that the properties of empty space are the same in all directions. Earlier we said space is homogeneous. In other words, the location didn't matter, the absolute location of the origin didn't matter. Now we are going one step further and saying space is three-dimensional and is isotropic, has the same properties in empty space in the absence of all matter and so on. It has no fields, nothing of the sort. The space itself is the same in all directions. Its properties are the same in all directions. So this arises from the isotropy of space. That is the deep reason for the conservation of angular momentum when the circumstances are right. Once again, this can be broken. This principle can be broken. The conservation can be broken or violated once you violate the isotropy of space by having some field present. Exactly as in the case of the linear momentum, we will look again at the example of the projectile. So here is the projectile. I project it with some initial velocity and it takes a parabolic path and falls down here, and that is the origin of coordinates. Now the question is, what about the conservation of angular momentum of this projectile? The answer is it is certainly not conserved, because you can see that at the initial instant of time this was the momentum and that was the position. It happened that r was equal to 0 in that case. So L is equal to r cross p happens to be 0 initially, but when the particle is somewhere here, for instance, that is the direction of p, this is the direction of r in this direction, and r cross p goes into the board and it is not 0. So clearly r cross p is not conserved in this case, because the isotropy of space is broken. It is broken by the fact that this direction, the vertical direction, has a field in it, the horizontal direction does not have a field in it. So this property of space being exactly the same in all directions is no longer true. The moment you have a force of this kind, you have broken the isotropy of space, and therefore angular momentum is not conserved. It is only when you have this isotropy of empty space and your physical conditions do not break this isotropy that you have the conservation of angular momentum. In this problem itself, when I say space has exactly the same properties in all directions, and if you have a force in it which also has the same property, that it's the same in all directions and only depends on, say, the distance from some attracting center, then angular momentum is indeed conserved. And we know that in this case this is an approximation to the fact that you have the earth, which is supposed to be a sphere, and the laws of the force of gravitation at this point acts directly inwards. The force of gravitation at this point acts directly inwards, and in this case, if you take this to be the origin of coordinates, these field lines are all going to focus inwards towards the center of the earth, and the magnitude of this force does not depend on where you are on the surface, only on the distance you are from the center of the earth, and that is a radial distance which is purely the radial coordinate. In this case, the force of gravity is equal to g times the mass of the earth times the mass of your little body divided by r squared, where r is the distance to the center of the earth, multiplied by the unit radius vector r in the radial direction. So let us call it r squared, the distance from wherever you are to the center of the earth, with a minus sign to show that this radius vector, this force is opposite the radially outward vector, unit vector. Okay. There is no angular dependence. There is no dependence on the latitude and longitude in this case to this approximation of a perfectly spherical earth, and therefore this force here is radially directed inwards and depends only on r and not on the polar angle theta or on the azimuthal angle phi. It does not depend on those quantities. In spherical polar coordinates, it does not depend on theta, does not depend on phi, depends only on r. This sort of force directed towards the center of the earth or center of attraction is called a central force. Now a central force does not have any angular dependence at all, and therefore respects the fact that in all directions as far as the angles are concerned, there is no dependence, the force is exactly the same. Therefore, in such a situation, when this is the force on a body, you would expect the orbital angular momentum of that body about the center of attraction, about the origin of coordinates, to be a constant of the motion. And indeed we know that when a particle goes, for example, in an elliptic orbit around the Earth, we know that this quantity, L is r cross p, is a constant of the motion. It's only when you make this approximation of parallel field lines and there's a flat Earth and there's an origin here, and you look at the angular momentum about this origin, that you say that its x and y directions are not equivalent to each other, and therefore there is no angular momentum conservation. But in reality, if you look at the actual central force of the gravity due to the Earth, then indeed about the origin, about the center of the Earth, there is angular momentum conservation. It is true that as a particle moves in an elliptic orbit, its orbital angular momentum about the origin, about the center of attraction, which is at one of the foci of the ellipse, is a constant of the motion. Definitely, that's true. So one should understand the origin of these conservation principles. They arise ultimately from deep properties of space, linear momentum because of homogeneity of space, and angular momentum because of the isotropy of space under the right conditions. Now you could immediately ask the natural question, where does the conservation of energy come from? In those cases where it is applicable, where does this energy come from, conservation come from? The answer again is buried in an invariance principle, and I will state it in words but without any effort to prove it here. It's a good idea to know the reason why, even if you cannot prove it at a certain level. And the conservation of energy, I'll just erase this. Energy arises from, well, we've exhausted the isotropy of space, the equivalence of all directions in space, and we've exhausted the homogeneity of space. There's one more variable in dynamics, and that's time. So this arises from the homogeneity of time. When you have rules of evolution or rules of change or equations of motion which do not depend on the absolute origin of time but are exactly the same even if you shifted the zero of your clock arbitrarily, then you have the potential for the conservation of energy in suitable conditions, under suitable conditions, exactly as in the case of the other conservation principles. So again, I want to emphasize that these are deep principles and properties. These arise from deep properties of space and time themselves, and when those properties are refined further, then there are suitable modifications to these principles, or they apply under more general conditions and so on. But ultimately, these conservation principles arise from the fact that the equations of motion do not change if you make certain transformations on the coordinates, on the variables, space and time variables, provided you have the invariance already built in, provided you have the fact that in the case of conservation of energy, for example, if you do not have explicitly time-dependent rules of evolution for these variables, then it doesn't matter when you start the zero of time, the origin of time. And in that sense, the homogeneity of time can lead to the conservation of energy. We'll see what the consequences of these conservation principles are, because we need a good application for this. And a very good place to look for an application is a problem that's actually very complicated, but which can be made simple as far as practical considerations are involved. It can be made simple by applying conservation principles. And I have in mind the standard problem of the collision of two bodies. To start with, let's look at just two bodies. That's the simplest case. So you have some hard mass here, some mass m1, and it's moving along and it collides with a mass m2. And after the collision, these two particles go off. So we have in mind a situation where the two particles, it's most convenient to think of them as particles, would undergo an elastic collision in the sense that there's no loss of energy or anything like that. The total initial kinetic energy is equal to the total final kinetic energy. But what actually happens in the collision process is very complicated. We don't worry about it. It happens very quickly, but what we do is to say that, all right, here's some region in which the particles collide. One particle goes in with some momentum m1, with some momentum p1, and m2 with some momentum p2. They collide, bounce off each other, and out go two more particles out here. So this is m2 with a new momentum p2 prime, and this here m1 with some momentum p1 prime. That's the standard collision problem. And we ask the following question: given p1 and p2, and of course the masses m1 and m2, can we say what p1 prime and p2 prime are going to be without knowing very much about what's going on inside this region of interaction? In a very short time there's a little collision, and then for some reason they collide and they scatter out due to some complicated interaction, and they move on their way, and afterwards there's no force on them. So by the first law, p1 is constant till the interaction occurs, as is p2, and then after the interaction p1 prime and p2 prime remain so forever. In other words, the particles move in straight lines with the final momenta. So the question is, can we discover what these quantities are given these two quantities based on conservation principles? This is the problem of collision kinematics, or two-body scattering. Scattering is another word for collisions. Can we discover this at all? Well, as always, we should look at a simple case. So let's first look at the case where these particles collide and separate in the same line. So this is a very special case, and it happens under certain circumstances. So we'll look at the simplest instance where a particle comes along in this fashion, m1, with the prescribed initial momentum p1. Since I'm only going to look at this line, I don't even draw a vector. If p1 is positive, it's moving this way. If p1 is negative, it's moving the other way by convention. And it hits a particle which is moving with p2, momentum p2, in the same direction. But actually you can do an even simpler problem, and that is to say this is a projectile of mass m1. This is the projectile of mass m1, and it hits a stationary target, a mass m2, which is the target particle. This is before collision. So this particle comes along at a constant momentum p1, hits this particle in an infinitesimal interval of time. Something happens to the two particles, and then they separate out once again and move along with constant velocity. So this is before collision. And after collision, since we have assumed it to be in the same direction, this was the initial direction. After collision, in general you would expect this particle 1 would bounce back and transfer some of its energy to m2, which would move out there. So let's call this m1 p1 prime, and the other particle goes this way, and that's m2 p2 prime. So what we have done is to set p2 equal to 0 without loss of generality. The target is stationary in the laboratory frame, and the projectile comes along, hits it, and then they separate out here. Now if p1 prime is negative, it's moving this way, but it's conceivable that if you have a very heavy particle coming along, it will push this and both will move in the forward direction. It doesn't matter. It doesn't matter. We can consider both cases in one shot. So the sign of p1 prime will determine whether it's moving backwards or moving forwards. And p2 prime you of course expect on physical grounds intuitively to move forwards and not backwards, because there's no initial momentum in this direction at all. Okay. Now how are we going to solve this problem? We use Newton's third law, which says the rate of change of momentum is equal to the force on the body, right? Therefore we know that the force exerted by particle 1 on particle 2 is minus the force exerted by particle 2 on particle 1. Therefore we know that the change of momentum, we know that p1 prime minus p1, that's the change of momentum of the first particle. The change of momentum of the second particle is just p2 prime minus 0, so it's just p2 prime, and we know that p1 prime minus P1 times delta t, the time of collision here. This is equal to, so rate of change, so let us say over delta t, does not matter in that case, over delta t is equal to the rate of change of momentum here, P2 prime minus 0 divided by delta t with a minus sign, because we know that F12 equal to minus F21. This is F12, the force due to 2 on 1 is the change of momentum, rate of change of its momentum, and the other guy is this out here. Okay. So the delta t's cancel out in this problem, and this will immediately imply that P1 is equal to P1 prime plus P2 prime. So the total momentum before the collision is equal to the total momentum after the collision, the algebraic sum on either side. This is conservation of linear momentum. So in future, I am not going to go through this argument about Newton's third law. I am going to write the conservation of momentum down automatically, because you can easily convince yourself very trivially that even if P2 had not been 0 but had been some value on the same line, it won't matter. You would get P2 prime minus P2 here, and this would become P1 plus P2 is P1 prime plus P2 prime, and momentum is conserved. So henceforth we will simply write down momentum conservation in such situations without going through the argument involving Newton's third law. But you must remember that it comes from this argument, and it is independent of the actual details of the force, because the assumption is the force acts for an infinitesimal time delta t, and after that these are free particles moving according to Newton's first law. That is all that is important. And the third law has been built in, has been put in. In writing this step, the second law has been built in. And in saying that they move freely after the collision in straight lines with given momenta is the first law once again. So all the laws of motion have been put in understanding this collision problem. Now we are going to use this principle, and we are going to use this principle, the conservation of energy, because we haven't written down that yet, in order to solve this problem. And what do we need to solve? Given P1, to find P1 prime and P2 prime. In other words, how is the momentum, initial momentum, divided up between the target and the projectile after the collision? And then once you know the momenta, you know the kinetic energies, so we could ask how much energy is transferred from the projectile to, say, the target. And this is what we are going to do next.